This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today's paper, GSCE, a prompt framework with enhanced reasoning for reliable LLM-driven drone control, tackles the reliability issues inherent in using large language models, LLMs, for drone control. Let's start with the core problem. Why is using LLMs for drone control so challenging?
The challenge lies in the inherent limitations of LLMs in complex reasoning, especially when precise action sequences are crucial. Unlike text generation, where semantic accuracy suffices, drone control demands precise code execution. Incorrect code can lead to dangerous drone behavior, including crashes. Existing methods often rely on prompting with guidelines and APIs, but this approach lacks robustness for complex scenarios and is susceptible to errors in API selection or usage.
The paper proposes a solution called GFCE. Can you elaborate on its components and how they address these limitations?
GSCE is a structured prompt framework comprising 4 key components: guidelines, skill APIs, constraints, and examples. Guidelines define the LLM's role and coding style. Skill APIs provide documented drone control functions. Constraints enforce domain-specific rules and policies, addressing situations where the LLM lacks prior knowledge or specific implementation requirements are needed. Examples, crucial for in-context learning, demonstrate how task descriptions map to code, including constraint implementations.
How does the inclusion of constraints within the examples enhance the LLM's reasoning?
Simply providing constraints as text often proves insufficient. LLMs can be prone to ignoring or misinterpreting them. By explicitly incorporating constraints within the example code and annotating them with comments, GSCE forces the LLM to learn how to correctly implement these constraints. This significantly improves the reliability of the generated code.
The paper mentions chain of thought COT reasoning. What role does it play in GSCE?
COT encourages step-by-step reasoning. In GSCE, examples are structured to demonstrate COT, breaking down tasks into sequential actions. This helps the LLM learn to decompose complex tasks into manageable steps, improving its ability to generate correct and complete code.
The experimental setup involved various tasks of differing complexity. What were the key findings regarding the performance of GSCE compared to baseline methods?
The experiments showed a dramatic improvement in both success rate and completeness using GSCE. The baseline method, relying only on guidelines and APIs, performed poorly. Methods incorporating either constraints or examples showed improvement, but GSCE, combining both with COT in the examples, achieved over 90% success rate and completeness. This highlights the synergistic effect of all 4 components.
The paper also explores the impact of the number of examples. What were the key takeaways from that analysis?
Increasing the number of examples generally improved performance, but the gains diminished beyond 3 to 4 examples. This suggests an optimal range for balancing performance and computational cost. Using more examples increases the OpenAI credit consumption, so a balance is needed.
What are some limitations of the current GSE framework, and what avenues for future research does the paper suggest?
One limitation is the reliance on predefined constraints. Future work should explore adaptive constraint learning, allowing the system to adjust to dynamic environments. Another area is integrating multimodal inputs, such as images and LiDAR data, to enhance the LLM's situational awareness and decision-making.
The paper highlights the importance of a structured prompt engineering approach for reliable LLM-driven drone control. The GSCE framework offers a significant advancement in this area by combining guidelines, skill APIs, constraints, and examples with COT reasoning. This discussion has been insightful. Thank you.